So in our last video on molecular geometry, we learned how to use Lewis structures to predict what 3D arrangement of the atoms we think we would see. In today's video, we are going to be looking at what's called molecular polarity, how we can determine the polarity of a molecule based off of our knowledge of their shape and Lewis structure. And so to start us off, there are two factors that affect molecular polarity. The first thing is going to be this idea of bond polarity. So that's pretty self-explanatory, but really what it's looking at is the polarity found within individual bonds. And the second thing that we're going to be looking at is going to be this idea of the molecular shapes or the valence shell electron pair repulsion, which is what we covered in the last video. So let's start by looking at bond polarity. And bond polarity is often referred to as what we call a dipole. So you're going to hear that a couple of different times throughout this year. What that basically means is that within a polar bond, we know that there is a larger difference in electronegativity between the two atoms within that bond. And so one of the atoms is going to be pulling more strongly on the electrons in the bond than the other atom. And so that's going to create what's called a dipole. And what that means is it's an instantaneous unequal distribution of electrons in a polar bond. So we can represent that unequal distribution of the electrons in a polar bond. I'm going to actually go ahead and get rid of this word instantaneous. Let's just focus more so on the unequal distribution. But we can represent that by using an arrow. And the arrowhead is always going to point towards the more electronegative atom. So if we were to look at a bond between hydrogen and chlorine, we know that chlorine is much more electronegative than hydrogen is. And so our arrowhead is going to point towards the more electronegative atom. So we draw it pointing towards chlorine. And the other end is going to have a plus sign, because what this means is the electrons are really being dragged this direction by the chlorine because it's pulling more strongly on them, which again leads back to that unequal distribution in the polar bond. And what it ends up creating is an overall partial, so that's what this lowercase delta means, is partial negative and partial positive charges within the bond. And that is how our dipoles get created. So we can determine if there's a dipole within an individual bond, but what we also need to be able to do is determine an overall polarity of a single molecule. And so in order for us to do that, we have to look at all of the dipoles that could form within the different bonds of that molecule. And so here are a couple of steps to help us do that. So the first thing we always need to do is draw out our Lewis diagram. And then from that Lewis diagram, we need to determine what the valence shell electron pair repulsion shape would be, and to put a dipole on each bond. So if we look at our Lewis diagram here, we're looking at a molecule we've seen a couple of other times. So we're looking at boron trifluoride, and the Lewis diagram is already drawn for you. What shape from our last video is boron trifluoride? So hopefully you've realized that there are three electron domains on boron trifluoride, which means that it has an overall trigonal planar shape because there is no lone pair on that central atom to push it into the trigonal pyramidal shape. So our valence shell electron pair repulsion shape would be trigonal planar. And then our next step is to draw the dipoles on each of the bonds in the molecule. So we have to use our electronegativities, our electronegativity trend or the electronegativities on your periodic table to figure out which of the atoms is more electronegative. So when we compare boron to fluorine, we know that fluorine is more electronegative, so the arrowhead is going to point towards fluorine in all of these examples here. And towards boron, we know we're going to have that slight positive charge because the electrons are being pulled away from boron. So then the next thing we have to ask ourselves is this big question down here. do these bonds cancel out? Are the electrons being pulled away from the central atom in a way that they are being canceled out? And the answer here is yes. And so since they are being pulled in equal directions away from the central atom with the same amount of force, we would actually say that this molecule is what we call a symmetrical molecule. It looks the same throughout the whole thing, and it's pulling the dipoles are canceling each other out. And so that's how we can use our idea of bond polarity and apply it to molecule polarity to determine whether or not a certain molecule is going to be polar or nonpolar. So let's go ahead and walk through another example together about determining molecule polarity. So this is one, again, we should be very familiar with. We've got a molecule of water. So our first step is to draw the Lewis structure. So remember from our Lewis structure video, the first step of drawing a Lewis structure is coming up with your electron tally. So I know I have 2 hydrogens, and each hydrogen is contributing 1 valence electron. And I've got 1 oxygen, and that oxygen is contributing 6 valence electrons to give me a total of 8 valence electrons to use in my Lewis structure. And then I have to draw my central atom. So since oxygen has 6 valence electrons, and I know from the Lewis dot diagram that it can form 2 bonds, whereas hydrogen has 1 valence electron, so it can only form 1 bond. Oxygen is going to be our central atom. And I start by forming my single bonds to the hydrogens from the oxygen. Each single bond takes up 2 electrons. So from my 8 valence electrons, I have to subtract 4, leaving me with 4 electrons left over. Those hydrogens are exceptions to the octet rule, so they are happy with the number of electrons they have. So those 4 extra electrons are all going to go onto the oxygen so that oxygen 2 can satisfy the octet rule. So that's our first step, is drawing our Lewis structure. Our next step is to determine what the valence shell electron pair repulsion shape would be. What is the molecular geometry? And so since there are 4 different electron domains, we've got 2 domains that are bonded, and we've got 2 domains that are lone pairs. We know that we are going to be looking at a shape similar to a linear shape, but we have to again remember that these lone pairs up here on the oxygen are going to repel more strongly, so that instead of it being linear, we're going to end up having what we call our bent shape. And then our last step is to look and see about the bond dipoles, our bond polarity. So we have to draw those dipoles overall. I'm just going to clean up the image just a little bit so that we can draw our dipoles and see them pretty clearly. I'm going to draw those dipoles in red. So we have to look at our periodic table and figure out which element is more electronegative. And in that bond between hydrogen and oxygen, oxygen is more electronegative. So our arrowhead points towards the oxygen with that slight positive charge at the end near the hydrogen. And so all of these electrons are being pulled towards the oxygen. And so when we go to ask ourselves this big question of, do these bonds cancel out? Here we're going to have to answer no, because all of the electrons in the molecule are being pulled in one direction. And so if they're being pulled in one direction, and the bonds are not canceling out, we would have to say that this is going to be a polar molecule overall. Whereas the example before, where we were looking at our boron trifluoride, we would call that a non-polar molecule. So let's go ahead and do one more example together where we're looking at molecular polarity. So remember, our first step is to draw the Lewis structure. So I've got 1 carbon, and each carbon can contribute 4 valence electrons. I've got 1 hydrogen, and each hydrogen can contribute 1 valence electron. And then lastly, I've got 3 chlorines, and each chlorine is going to contribute 7 valence electrons to give me a total of 26 valence electrons to work with in my Lewis structure. So looking at those 3 atoms, between carbon, hydrogen, and chlorine, carbon can form the most bonds, so carbon's going to be our central atom. I'm going to start by forming my single bonds to all of the other atoms, so a single bond to hydrogen since I have one of those, and then I keep wanting to write hydrogen, and then 3 single bonds to chlorine. So when I look at the number of electrons that are taken up in those bonds, I see that there are 8 electrons that I have to subtract from my electron tally. And when I subtract those, I end up having a total of 16 electrons left over, and not 16. I have 18 electrons left over. And so I have to disperse those 18 electrons evenly on the surrounding atoms, but I know that hydrogen has all of the electrons that it already needs, so I don't need to add any extra electrons to hydrogen. So I end up splitting up those 18 electrons on just the 3 chlorines. So 18 divided by 3 is 6. And so I go ahead and place those 6 extra electrons on each chlorine. And then just to check myself, I need to make sure that each atom in the compound or in the molecule satisfies the octet rule. So hydrogen, remember, was our exception, that it can only hold 2 electrons. So hydrogen satisfies the rule. Each chlorine has 6 of the electrons from the surrounding plus the 2 that are in the bond. So each of these chlorines are going to satisfy the rule. And then lastly, our carbon has 2 electrons in each of those single bonds, so it has a total of 8 electrons overall. And again, I'm going to go ahead and just clean some of this up so that we can move on to the next part. So our next step is to determine the overall shape. And so since this has 4 electron domains, and all of those domains are the same, they're all bonds, they're going to be repelling each other with equal amounts of force, but remember, it's not really a circle. We have to think about this as 3-dimensional, but regardless, since we have 4 bonded domains, we are looking at a tetrahedral molecule. And then our last step is going to be looking at the bond dipoles that exist. So clean it up one more time. So if we're looking at the bonds between carbon and chlorines, chlorine is going to be a lot more electronegative than carbon is. So our arrowheads are going to point towards the chlorines, and that partial positive charge is going to be pointing towards the carbon end. And so we do that for all 3 of them. And then lastly, we have to look at the electronegativity between carbon and hydrogen, and carbon is more electronegative than hydrogen is. So the arrowhead is going to point towards carbon and away from hydrogen this time. So then we go back to that big question of, do these bonds cancel out? So if I were to look at the top and bottom bonds, and it doesn't matter where you drew your hydrogen here, but if I was to look at the 2 chlorines, I'm going to highlight them. If I was to look at these 2 chlorines here and here, those 2 chlorines are pulling away from the carbon, the electrons that are in the bonds between them and the carbon. They're pulling away from the carbon with equal amounts of force. So these 2 bonds, we would say, do cancel each other out. So I'm going to do this part in blue. So these bonds do cancel each other out. But we have a couple of other bonds we have to look at as well. So the next bond we're going to be looking at is going to be this chlorine to the hydrogen. And here we see that these electrons are being pulled in the same direction by the atoms. So I would say that these 2 bonds, I'm going to do these parts in black. So here and here, these bonds do not cancel out. And so if they do not cancel out, we have an overall pull of the electrons in a single direction, which means that this molecule is going to be polar. So overall, summarizing this, how does symmetry affect polarity? So symmetrical molecules are going to be nonpolar. So if we can identify if a molecule is symmetrical or asymmetrical, that is going to help us with determining the polarity. So looking here, we've got a couple of different structures. So the first structure we're looking at is a linear structure. The second one is going to be our bent structure because we have the two bonded domains plus the lone pair. Then we've got our trigonal planar structure because we have the three bonded domains. Then we've got trigonal pyramidal because we've got the three bonded domains plus the lone pair. And then lastly, we have our tetrahedral molecule. So if we had to identify which of these were going to be symmetrical versus asymmetrical, the symmetrical ones are going to be, that's not what I wanted to do. The asymmetrical ones are going to be the linear molecule, the trigonal planar molecule, and the tetrahedral molecule. And I'll give you guys a little bit of a key down here. So the yellow means symmetrical. And anything else that is not yellow is going to be asymmetrical. So if we can draw the Lewis structure and identify the molecular geometry and determine if it's symmetrical or asymmetrical, we can also determine the polarity.